Guys, welcome to your lab for the photoelectric effect. So the explanation of this photoelectric effect is actually what Einstein won his Nobel Prize for. That might come as a surprise to some of you, because whenever you think of Einstein, you think of maybe general relativity or special relativity. But really, this was Einstein's crowning achievement, and this is what gained Einstein notoriety at the time in the field of physics. So let's first talk about what the photoelectric effect is, and then we'll talk about the explanation behind, or the physics behind what's happening with the photoelectric effect. So what the photoelectric effect is anytime we shine a light ray, so this is light coming down, onto a metal surface, we see some electrons being ejected. Now this isn't hard to understand because we know, and at the time it was thought, that light was a wave. And so this light wave is going to have some energy, and when it strikes the electrons in this metal plate, it's going to transfer its energy to those electrons, and then they'll be liberated from the surface. What was unusual and what was unexplained was no matter what the intensity of this light was, we always saw some electrons being ejected. Now this was counterintuitive because you would think at some low intensity, at some threshold of energy, you would expect to see no electrons being emitted because they were still bound tightly within the metal. So how we explain this, or how Einstein explained this, is to say that, okay, light is not just a wave, but it also behaves like a particle. And these particles of light, known as photons, have an energy equal to Planck's constant times the frequency. So when these particles of light are incoming and they strike these electrons, they transfer their momentum to the electrons, and then the electrons are ejected. This explains the issue with the intensity, because when we decrease the intensity of the light, no longer are we thinking about the energy being decreased, but we're decreasing the number of photons. All right, so when we decrease the intensity, we have less photons coming and striking it, but we still will see some electrons because the photons themselves are not losing energy. Right? We just have less of them. Okay, and what we want to do is now use this information in order to solve, or to experimentally determine what Planck's constant is. And we can do this by writing the equation for the conservation of energy for this system. So the energy of these electrons outgoing from this metal have to be equal to 1/2 mv squared, which is just the kinetic energy of the electrons, and that has to be equal to the energy of the incoming photon, hf, minus what's known as the work function for our metal. Now the work function is the minimum amount of energy that we have to add to the electrons in this metal in order to eject them. Okay, it's not. It can sometimes take more energy in order to eject these electrons, depending on where the electrons are located within our material. If the electrons are held deeply within inside, it may take more energy, more than the work function, in order to eject that electron from our material. Okay, but the work function is the minimum amount. So if these electrons are loosely bound on the surface, that's the minimum amount of energy that we have to add to those electrons before they will be liberated. Okay, so that's why it comes with a negative sign, because we have to subtract that off from the energy of the photon, and whatever is left over is transferred to kinetic energy. So this means that the electrons that come off the surface of the metal are going to have some range of energies, right? And their energies are going to range from 0 to hf minus the work function. So the maximum energy that these electrons can have is hf minus the work function, and of course the minimum amount of energy that they can have is 0. Okay, so what we're going to do in this lab is, if we can determine what the energy of these outgoing electrons are, we can then graph that energy versus the frequency of the incoming light, and then from that graph we can determine Planck's constant by just finding the slope. Now the issue is determining the energy of these outgoing electrons, right? Because we can't just measure this velocity directly. You can't just take a speedometer, put it next to this surface of this metal, and then measure the speed of these electrons. Instead, what we have to do is find the amount of energy that it takes to stop these electrons from traveling upwards. And we do that by taking a collector here, hooking it up to a variable voltage supply. That's what this is. We can change the voltage that we're supplying to our collector. And we're going to supply a reverse bias, which means we give this a negative charge. Okay, and depending on the amount of negative charge we give this, we're going to filter out some of these electrons, right? If this is the potential of that we supply to this collector is high enough, these electrons that are leaving this surface aren't going to have enough energy to overcome the potential difference, and they're not going to reach the collector. They're going to be forced back down before they can collide with the collector and then travel and be counted. So if we graph this, if we graph what's happening here, with our reverse bias on our X, and our output signal on our Y, what we expect to see initially when our reverse bias is 0 is that we have a very high output signal, because all of the electrons that we're exciting are going to be able to reach the collector here, because we haven't filtered any of them out yet. So initially, this is going to be very high. As we start to increase this reverse bias, we're going to start to filter out some of these lower energy electrons. So our signal is going to decrease. And as we continue to increase this reverse bias, eventually this output signal is going to level off. That means we've now filtered out all of these electrons. We've filtered out all of the electrons, including the ones that have this maximum amount of kinetic energy. So what we want to do is find out, where does that happen? Where does this begin to level off? Because that's going to be the potential at which all of the electrons are being filtered, and that means that potential is going to be equal to this maximum amount of kinetic energy. So where this begins to level off, at this point here, we call that the stopping potential. So that's the potential at which we're filtering out even the maximum kinetic energy. So that's the potential that's will be equal to this maximum amount of kinetic energy. So we can do this for different frequencies. So we'll have 4 or 5 different graphs that look like this, and each frequency will have a unique stopping potential. And then we're going to come over here and graph stopping potentials versus the frequency. So we have frequency on our x-axis, and we'll have the stopping potential for each frequency on our y-axis. Right, so basically what the equation that we're graphing here is going to be the stopping potential in EV, which is electron volts, just a unit of energy. That has to be equal to HF minus the work function. So that we're going to get a graph, and it's going to be linear, and it's going to look something like this, right, with different points for each frequency that corresponding to different stopping potentials that we got from these graphs here. And from the slope of this line, you can see that we'll get Planck's constant, right? Because this is our y, our stopping potential. F is our x, which means h is our m. And you can also determine the work function from the y-intercept. So if we extend this graph down and find this y-intercept, that is the work function of the material that we're using. That's going to be this lab. So that's all we're doing, is we're finding these stopping potentials for each of the different frequencies or wavelengths of light that we're viewing, and then we graph those stopping potentials versus the frequency, and from that graph we can then determine an experimental value for H. And so that's what you'll see in this next part. We'll go over how you would have used the equipment in order to determine these stopping potentials in lab had you been here to complete it. Okay guys, here's the setup for the Photoelectric Effect lab. Here is our light source that is shining into our photo tube here, right? So this is the light source that's going to be exciting electrons into here. We can then take the output from there, so you can see on the back here, we take this output voltage, or we take the current, the photo current that's being outputted, and then we run it along this wire to the back of our power supply here, and it's going to measure the current here, or it's going to display that current here, and this is where we're going to be supplying our output voltage. So this is our output signal that we're measuring, and then this is the reverse bias that we are supplying to our collector. All right. One other thing is on the top here, you can see that this is where we're going to be able to apply different filters in order to be able to get different wavelengths and frequencies of light. So right now we are set to measure the stopping potential of a wavelength of 546.1. That would be in nanometers, would be the wavelength for this particular filter, right? And we have different filters. Let's go. We can go ahead and change it so you can see how it's changed. You just turn it, and now we have a filter that's gonna filter out and leave only 577 nanometer wavelength light. Okay. We're gonna have this set about 30 centimeters away from our light source here, and let's go ahead and show you how you would take data. Alright, so I told you that this is going to be our output current, and this is going to be the reverse bias voltage. So you can see we already have our reverse bias set to 2 volts. So we're actually going to do this backwards. We're going to start with, instead of going from 0 to negative 2 volts, we're going to start with 2 volts and then go to 0 instead, just because it's easier to take our data this way. Alright, so as we're going to increase this or decrease our reverse bias by 0.05 volts. So we're going to have quite a bit of data. So let's go ahead and do our first data point. We'll decrease that to 1.95 volts. We'll wait for this current to level off, which it doesn't take long at this point. And then we will record this current. And our units are here, 10 to the minus 13 amps. All right. And now we would go on to the next voltage. So we, instead of 0.95, we just move this so it's 0.90, and then again re-record our current. Now we're not expecting this current to change because we're at the part of the graph for the input versus reverse bias voltage where we're at the plateau. Right, we at these higher reverse biases, we don't expect to see much of a change with our output signal. So let's go ahead and change it a little bit more, just to give you an idea of what it might look like. Maybe 1.5-ish. Okay, still no change. Let's change it a little bit more. Okay, so I guess we still have no change. Let's just keep going. Here we go. All right. So now we're at a reverse bias of 0.5 volts. And we can see that we're starting to get some positive amount of current now. So we're getting a larger signal. Let's wait for that to level off some. It does take a little while, so every time that you change your reverse bias, you have to wait for the current to kind of come up and level off. Alright, so this would be 256 times 10 to the minus 13 amps. That would be our signal for this reverse bias. And then we would just keep going in steps of 0.5, from 2 all the way up to 0, recording this current each time. And then once we finish going from 2 to 0, we would just come over here. All right, change our filter to a different wavelength. So this one is the 365 nanometer wavelength. Let's make sure that this goes back to the minus 2 volts, which is where we're going to start for each time. There we go, close enough. All right, and then we would wait for this to come to a level, and then we would again begin to decrease our reverse bias by 0.05 each time, taking the signal output at each voltage reading. Okay, and that's how you would record data for this lab. So hopefully that makes sense. The data that we has already been recorded and is on Canvas for you. So go ahead and use that data. Make sure you understand why it looks the way it does, and then from that you'll be able to write your lab report. Okay guys, see you next time.